one of today's most notable and sophisticated physicists, has shared his views on the subject. Michio Kaku, renowned for his remarkable contributions to the discipline of physics, has recently affirmed that the James Webb Space Telescope has identified 6 substantial galaxies that scientists previously believed could not exist. These investigations possess the potential to unlock new dimensions in our comprehension of the cosmos, making it an exhilarating development that merits attention. Kaku stands as a prominent figure in the scientific community, a physicist of both American and Japanese heritage, recognized as an authority in classical experimental physics and quantum mechanics. Unlike certain more traditional and skeptical scientists, Kaku does not align with that group. Instead, he has been receptive to the astonishing outcomes of the James Webb Space Telescope mission. We are pleased that this distinguished scientist has chosen to break his silence and openly share what can no longer be contested. The enthusiasm and almost amused demeanor of the esteemed stellar physicist are palpable in his remarks regarding the discoveries made by the James Webb Space Telescope, highlighting that this has been the focal point that has captured his curiosity. Join us in exploring the ramifications of Kaku's discovery of these 6 massive galaxies. Kaku is a scientist who has consistently been open to considering new theories throughout his career. He recognizes that Einstein's equations of relativity and Newton's laws do not sufficiently encapsulate the universe's full intricacy. Kaku acknowledges that the revelations from the new telescope may enhance the scientific field, despite many of his peers being unable to adopt this perspective. This has sparked anxiety and sleeplessness among supporters and detractors of quantum mechanics. Yet such concerns elicit only laughter from Kaku. The James Webb Space Telescope has unveiled the existence of 6 enormous galaxies dating back to the universe's earliest epochs. Each of these galaxies boasts a greater number of stars than our Milky Way, despite having formed merely 200 to 700 million years after the Big Bang. The astronomers responsible for this discovery have labeled these extraordinary galaxies universe breakers, as they confirm a need to revolutionize our entire understanding of the cosmos. Something seems amiss. The Big Bang theory suggests that the universe was a chaotic mass post-initial event, with solid objects taking hundreds of thousands of years to materialize. It was believed that it took hundreds of millions of additional years for these objects to achieve sufficient density and emit light. The emergence of complex structures like galaxies was assumed to occur much later. Some of the newly discovered galaxies surpass the Milky Way in size, and their immense brightness suggests they were likely forming hundreds of new stars annually, whereas our galaxy produces stars only sporadically. It remains uncertain when the first galaxies truly formed, as researchers have yet to ascertain this. What is evident is that initially, there may have only been individual stars or clusters that eventually merged into larger aggregations, leading to the formation of dwarf galaxies. These small galaxies encountered one another and gradually expanded. According to previous theories, highly organized and massive galaxies could not have existed during that era, prompting the question of whether the universe is significantly older than previously believed or whether complex large-scale galactic structures emerged much earlier. This situation poses a challenge for conservative science, which continues to grapple with this model, while some branches of physics are reluctant to accept this discovery, questioning potential inaccuracies in age calculations. Kaku is cognizant of this and remarked that there are numerous instances of outdated and erroneous theories that persist due to the prestige of certain scientists. Many of these theories were only discredited when a pivotal experiment unveiled their fallacies. Therefore, the foundational work in any scientific field, particularly in physics, relies on experimentalists who keep theorists accountable. In reality, we know very little about the true origins of the cosmos. The Big Bang theory was established in 1927, based on observations of the universe's expansion, leading to the conclusion that the cosmos originated from a singular point and has been expanding ever since. At that time, it was challenging for people and scientists to fathom a universe with a beginning and an end. The notion of a universe that has always existed and is infinite in time and space was beyond comprehension, and even today scientists struggle to grasp it. However, it is crucial to reconsider these probabilities. These new demonstrations do not align with the foundations researchers have relied on for decades concerning the Big Bang theory. Nonetheless, science has repeatedly shown that reevaluation and openness to new concepts are essential components of the scientific process, alongside the validation of certain theories and observations. As a child, I was taught that stars and planets were firmly anchored in the universe, each occupying a defined space. Today, however, we understand that everything in the cosmos is in motion. Planets orbit stars, stars travel within their galaxies at hundreds of kilometers per second, and entire galaxies swiftly navigate through the cosmos, the fate of which we cannot yet predict. Presently, scientists are confronted with the necessity of accepting uncomfortable truths and recognizing that theories are not merely educated guesses but not absolute certainties until they are rigorously tested or confirmed through precise observations. The concept of the Big Bang arose from the realization that galaxies are receding from one another, a distance that correlates with their distance from Earth. This observation, known as Hubble's law, suggested that the universe has been expanding. For a long time, elements such as cosmic microwave background radiation and the redshift of light from distant galaxies and other cosmological structures seemed to support this theory. However, it is important to remember that in the past, those who believed the Earth was flat and that the Sun revolved around us also had circumstantial evidence for their beliefs, until technological advancements provided a clearer and more accurate understanding. Currently, we find ourselves in a similar situation. Scientists anticipated that the new James Webb Space Telescope would corroborate assumptions linked to the Big Bang, but instead encountered these 6 galaxies that appeared impossible. This serves as a reminder that science is in constant flux, and researchers must remain open to new discoveries, reassessing existing theories based on the evidence available. Researchers employ redshift as a tool to ascertain specific quantities in the exploration of the cosmos. Redshift, also known as the Doppler effect, refers to the change in light color as the light source and the observer move relative to each other. To illustrate, imagine standing still and observing a car approaching you. As it nears, you hear the engine sound growing louder. Once the car passes or retreats from you, the sound alters, similar to how light behaves. When a distant star moves towards us, the light we perceive shifts towards bluer hues, whereas when it moves away, the light shifts towards redder hues. This phenomenon is termed redshift, and physicists have converted redshift values into velocities and distances for measurements in cosmic studies. It is essential to acknowledge that minor errors in these measurements can significantly impact outcomes. The measurement techniques previously employed are currently under scrutiny, and it will be intriguing to see what results scientists will derive. As for the latest findings related to our cosmos, it is vital to consider whether they truly stem from redshift errors or if some scientists are merely dismissing the facts. This query necessitates thorough analysis and careful evaluation of the data and methodologies employed in the research. As scientific inquiry advances, the revelations brought about by instruments like the James Webb Space Telescope frequently challenge our preconceived notions about the universe. The recent identification of 6 massive galaxies dating back to the early epochs of the cosmos serves as one such instance. These galaxies, which contradict conventional theories of galaxy formation, raise significant questions regarding the timeline and mechanisms involved in the evolution of cosmic structures. The James Webb Space Telescope, a successor to the Hubble Space Telescope, is outfitted with advanced technologies that enable it to delve deeper into space and observe with unprecedented clarity. Its capacity to detect light from the distant reaches of the universe grants astronomers a glimpse into the past, allowing them to study galaxies that formed billions of years ago. The discovery of these ancient and colossal galaxies challenges existing models, which predict that such large structures should have emerged much later in the universe's history. The implications of these findings extend beyond astronomy into the realm of fundamental physics. They compel scientists to reconsider established theories about the early universe, including the Big Bang theory, which posits that the universe began from a singular point and has been expanding ever since. While observational evidence such as cosmic microwave background radiation and the redshift of distant galaxies initially bolstered this theory, the discovery of galaxies that appear too mature for their age complicates this narrative. Michio Kaku, a prominent physicist known for his work in theoretical physics and popular science, has weighed in on these developments. Kaku, recognized for his ability to convey complex scientific concepts in accessible terms, acknowledges the transformative potential of the JWST discoveries. Unlike some of his more skeptical colleagues, Kaku embraces the idea that new observations should instigate revisions in scientific thought. He emphasizes the significance of experimental evidence in shaping our understanding of the cosmos, underscoring that theories must continuously evolve to accommodate new data. The debate ignited by these discoveries reflects the dynamic nature of scientific inquiry. On one hand, proponents argue that the detection of early massive galaxies suggests a longer timeline for galactic evolution than previously assumed. This viewpoint challenges the traditional understanding that galaxies gradually grew over billions of years through mergers and accretion of smaller entities. Conversely, skeptics advise caution against hastily discarding established models based on limited observational data. They advocate for a prudent approach, proposing that anomalies in data interpretation or measurement errors could potentially account for the unexpected findings. Redshift, a phenomenon observed in the light emitted by distant galaxies, plays a vital role in these astronomical explorations. As galaxies recede from Earth, the light they emit shifts towards longer wavelengths, a phenomenon known as redshift. By measuring the extent of redshift in a galaxy spectrum, astronomers can infer its distance from Earth and its velocity relative to our own galaxy. This data is crucial for constructing models of cosmic expansion and understanding the distribution of galaxies throughout the universe. The James Webb Space Telescope's ability to detect faint infrared signals allows it to observe galaxies obscured by dust and gas in the early universe, a crucial capability for studying star and galaxy formation during the universe's infancy, a period termed cosmic dawn. By analyzing the light emitted by these distant galaxies, astronomers can trace the chemical composition of the early universe and gain insights into the processes that facilitated the formation of the first stars and galaxies. In addition to its astronomical implications, the discovery of these early massive galaxies provokes philosophical inquiries regarding the nature of scientific progress and human comprehension. Throughout history, scientific paradigms have shifted in response to new discoveries and observations. What once seemed implausible or contradictory to established theories eventually becomes accepted as new evidence emerges. This iterative process of hypothesis, observation, and revision is fundamental to the advancement of knowledge across all scientific fields. The concept of a paradigm shift, popularized by philosopher Thomas Kuhn, describes the transformative change that occurs when anomalies in existing theories prompt a fundamental reassessment of scientific principles. The discovery of early massive galaxies challenges astronomers to reevaluate their understanding of cosmic evolution and the conditions that led to the galaxies we observe today. It emphasizes the importance of remaining open to new ideas and revising theories in light of empirical evidence.